Dear students, today we are going to discuss about the gravitational potential and the gravitational potential energy. Now you might be knowing that the earth has got the attracting properties. Now if we put now let me first define the gravitational field. Now if we put certain mass somewhere else, this mass has the ability to modify the space around it. This modified region around the given mass is known as the gravitational field. Similarly, now this modified region, for example, we have a mass m. This mass m modifies the region around it. That modified region around this mass is called the gravitational field. Now it is required to define the gravitational potential. To define the gravitational potential, let me consider an object of the certain mass. Let its mass be the m, mass m. Now this body is having the radius r. Now mass of body, this mass of body is capital M and its radius is capital R. Now let its center be O. Let me extend this line and let me take the point P on the straight line such that this point P is at a distance of r from the center of the mass capital M. Now let me now define the gravitational potential at point P. Now the gravitational potential at point P is defined as the amount of work done in bringing the body of unit mass from infinity to that point. That means we assume that the body of unit mass is initially at infinity. Now to bring this body of unit mass from infinity to point P, which is at a distance of r from the center of the bigger mass capital M, we need to do work. That work done to bring the body of unit mass from infinity to the given point P, this point, is known as the gravitational potential at point P. Now let me put the body of mass m at point P. Then the gravitational potential at P will be equivalent to Vp is equal to amount of work done, that is W, in bringing a body from infinity to point P. Now इस वर्क डन को हम डिवाइड करेंगे मास m से, where Vp comes out to be W by m. This is the definition for the gravitational potential at point P. Now if we put m equals 1, so we are left with Vp equals W. This means that the amount of work done in bringing the body of unit mass from infinity to the given point is known as the gravitational potential at a given point. Since this point is P, so we call this as gravitational potential at point P. Now, since work is a scalar quantity, therefore gravitational potential is a scalar quantity. This is a scalar quantity. Scalar quantity. Now its SI unit will be, now work is measured in joules and mass is measured in kgs, joules per kg, or its CGS unit is erg divided by kg is to be replaced by gram, erg per gram. Now its dimensional formula will be work. Now the dimensional formula for work is m1 L2 T minus 2, because work equals force into distance, m1 L1 T minus 2 into L1 divided by the mass, which is m1. Now on simplifying, we are left with m0, now L2, and this is T minus 2. This is the required dimensional formula for the gravitational potential. This is simply the definition for the gravitational potential and simply the parameters like SI unit, dimensional formula for the gravitational potential. Now let me derive the expression for the gravitational potential. See, expression for gravitational potential at a point. Expression for gravitational potential at a point. For that, let me consider the Earth to be a sphere of mass m. To be a sphere of mass m and radius r. Now this is the Earth with a radius r. Now let this be the center O. Let me extend this line. Let me take a point P on this straight line such that OP is equal to small r. Now it is clear that this r, that means the distance of this observation point P from the center of Earth, which is r is greater than the radius of Earth. Let me take 2 points on the straight line. Let me mark these 2 points as A and B, such that A to B distance is dx and O to A, let me take this distance as x. Now OP is equal to r, OA is equal to x, as you see from the diagram, and AB is equal to dx. AB equals dx. If we put a body of unit mass a body of unit mass at point A. Now this body of unit mass will experience the force due to this mass, that is due to the earth. Now I will write force acting on unit mass at A due to earth. That force can be written as, this is the gravitational force experienced by this unit mass at point A due to earth. Now I can write this as F is equal to G, mass of earth means m, unit mass which is 1 divided by the square of the distance separating point O and point A. Therefore this will be x square, and this can be written as gm by x square. This is the force acting on the unit mass at point A due to earth. This is actually the gravitational force. Now since we need to move the body of unit mass from infinity to given point, for that we need to do work. Let me now calculate, if the unit mass is placed at point A, let me now calculate the small amount of work done in order to bring a body of unit mass from point A to point B. That work done dW will be equivalent to F, this is the force, into the distance F dx. Actually expression is dW equals F dot dx. Since F and dx are in the same direction, therefore the angle between these two will be 0 and cos 0 is 1. Therefore simply we write dW equals F times dx. Now this is a small amount of work done in order to bring a body of unit mass from point A to point B through a small distance dx. Now replacing F by, this is G capital M by x square into dx. This is dW. Now the total work done to move a body of unit mass from infinity to point P without acceleration can be obtained by integrating this equation. Let me now integrate this as, this will be equivalent to gm by x square into dx. Now the limits of integration will be, we have to bring a body of unit mass from infinity. The lower limit will be x equals infinity. Now we have to move this body of unit mass from infinity to point P. Now the distance of point P from the center of earth is small r. तो यहाँ पर x लिखेंगे हमारा. This is the, now let me now integrate this equation. Now integration of 1 into dw gives w. This is w is equal to, now gm can be taken out of the integral, and inside we can write this as x raised to power minus 2 dx. Now limits will be infinity to r. Now let me integrate this equation. We are left with gm. Now integration means x raised to power minus 2 plus 1 divided by the whole power. So I can write minus 2 plus 1 gives minus 1. Here minus 2 plus 1 gives minus 1, or you can write in denominator whole power. This is infinity to r. So I can write this as minus gm, and x raised to power minus 1 can be written as 1 by x, and we can write this as infinity to r. Now this is minus gm. Now 1 by upper limit, that means 1 by r, minus 1 by infinity. Now you know that W equals minus gm, this is 1 by infinity is 0, therefore we are left with W equals minus gm by r. This work done in order to move the body of unit mass from infinity to the given point P is a measure of gravitational potential. It is the measure of gravitational potential at P. Therefore, I can write Vp equals minus gm upon r, which is the required expression for the gravitational potential at a given point, that is at a point P. Now see, Vp equals minus gm by r. Now Vp is equal to minus gm by r. From this equation we conclude that the gravitational potential at a point is always negative. Gravitational potential at a point is always negative. Is always negative. Now second, when r is equal to 0, when r is equal to 0, then gravitational, when r equals infinity, when r equals infinity, gravitational potential comes out to be 0. Vp is equal to 0. That is, the gravitational potential is maximum at infinity. Maximum at infinity. Now another point is, on the surface of earth, on the surface of earth, now we can write small r is equal to capital R. Therefore, the gravitational potential at the surface of earth, gravitational potential at the surface of earth, surface of earth will be equivalent to V is equal to minus gm by capital R. This is all about the gravitational potential and the expression for its gravitational potential. Now, let me now take another topic. Now, let me now see the another topic is gravitational potential energy. Gravitational potential energy. Gravitational potential energy. Now, to define the gravitational potential energy at a point, we need to define the position of zero potential energy. Now, that point or the position of zero potential energy is known as the zero level of the potential energy. Zero level of potential energy. Usually, that zero level of potential energy is taken as infinity, and at that reference point, at that reference level, the gravitational potential energy at that point, that means at reference level, is taken as the zero. Now, if the body is at the infinite distance from the another body, then the gravitational force on a body due to another is zero. When the gravitational force on this body due to another body is zero, that means the gravitational potential energy is zero, which is called the zero level of the potential energy. Now, if W naught is the zero level of potential energy of a body, zero level of potential energy of a body, zero level of potential energy of the body, and W is the work done in bringing the body, work done in moving a body from zero level of potential energy, to present location, then the potential energy of a body will be equivalent to W plus W naught, where W naught is the zero level of potential energy which is taken at the infinity, and W is the work done in moving a body from the level of zero potential energy to the present point, to the present location. Now, if initially body is at infinity, then the zero level of potential energy is equal to zero. That is, I can write W naught is equal to zero. Therefore, potential energy of a body that will be equivalent to W. From this equation, it is clear that the gravitational potential energy of a body at a point in the gravitational field of another body is defined as the amount of work done in bringing the body of given mass. In previous topic, in gravitational potential, we talk of a body of unit mass. But whenever we talk of the gravitational potential energy, we need to bring a body of certain mass. Let that mass be small m. Now, the gravitational potential energy of a body is equal to W. That means it is defined as the amount of work done in bringing a body of the given mass, let it be small m, from the level of zero potential energy, which is taken as infinity, from the level of zero potential energy to the given point. Therefore, we write, or you may write, the gravitational potential energy. You can write gravitational potential energy of a body at a point in the gravitational field of another body is defined as the amount of work done in bringing the body of given mass from infinity, or you can write from zero level of potential energy, from infinity or within brackets zero level of potential energy to that point without acceleration. Now let me find the expression for gravitational potential energy. Expression for gravitational potential energy. For that, again, we consider Earth to be a sphere of mass of Earth m and radius of Earth capital R. There is an Earth, there is center, and this much of distance is the radius, and I will write this as the capital R. Now let me produce this straight line, and let me take again the point P. This point P is at a distance of R from the center of Earth. Now, as is obvious, small r is greater than the capital R. Let me again take 2 points A and B such that A to B distance is dx. Now, we need to evaluate the amount of work done in bringing a body of certain mass, given mass, from the level of zero potential, that means from infinity, to the given point. Now let me consider that point as P, and you may write OA. Let me take distance as x, O as x. Now let me put the body of mass m at A. Now this body of mass m will experience certain force because of the gravitational field or because of the gravity of the Earth. Now let me write force experienced by mass m at point A. That force is given by the gravitation law F equals G, mass of Earth into mass of the body divided by x square. Now, let me calculate, same as at a previous article, previous question, small work done in order to move this body of mass m from A to B. Small work done to move a body of mass m from A to B, from A to B. That work done will be equivalent to dW equals F times dx. Now, replacing this F by G capital M small m x square into dx. Now, it is required to move the body from infinity or from the level of zero potential to the given point P. For that, we need to integrate this equation, that is integral of dW will be equivalent to g mm can be taken out of the integral, and we are left with 1 by x square, and 1 by x square can be written as x raised to power minus 2 dx. Now, the limits of integration are, here you have x equals infinity, because at infinity we can take the gravitational potential energy to be 0, x equals infinity to x equals this distance of point P from the center of Earth, that is r. Now, this can be written as W is equal to, when you will integrate this integral, you are left with minus G capital M small m by x by r. This is the amount of work done in order to bring a body of certain mass from infinity to the given point. This work done is equal to the gravitational potential energy. Gravitational potential energy. And we may write this as U equals minus G capital M small m by r, which is the required expression for the gravitational potential energy. Now, gravitational potential energy equals minus G mm by r. Now, let me have the analysis of this equation. Point 1, analysis. Now, I can write this equation as U equals minus G m capital M by r. I will put this enclosed within the brackets, and I will write here small m. Now, you might be knowing that minus Gm by r stands for the gravitational potential at a certain point. We write this as V into m. This means gravitational potential energy is equal to the gravitational potential into mass of a body. This is the first important point. That is, the gravitational potential energy is equal to gravitational potential into the mass of the body. Now, in this equation, let me mark this as equation, whatever you want, write x. Now, another important point. From equation x, it is clear that we have the gravitational potential energy with the negative sign. Now, this negative sign shows that the potential energy is due to the attractive gravitational force. Potential energy is due to attractive potential energy is due to the attractive gravitational force exerted by earth on a body. This is the significance of negative sign. That means negative sign in equation x indicates that the potential energy is due to the attractive gravitational force exerted by earth on a body. Now third point. We write third point here. As r increases, if the value of r increases, the gravitational potential energy also increases. As it becomes, if r increases, u also increases. As you see, when r will increase, the gravitational potential energy will become less negative. I will write here less negative. If r is equal to infinity, the value of gravitational potential energy becomes 0. That means maximum. If r increases, gravitational potential energy also increases. That means the u becomes less negative. When r tends to infinity, u becomes 0. That means the maximum. And another point. Now another point is this point number 4. If a body of mass m is moved from a point at a distance r1 to another point which is at a distance of r2, then the change in the gravitational potential energy of a body, that means delta U, that will be equivalent to integration of gmm by x square into dx. Since the body of mass m is moved from a point at a distance r1, now this will be r1 and this upper limit will be r2. Now on evaluating this equation, we are left with gmm then 1 by r1 minus 1 by r2. This is the change in the gravitational potential energy when a body of mass m is moved from a point at a distance r1 to another point at a distance r2. Then this will be the change in the gravitational potential energy. Now, if R1 equals capital R and R2 is equal to R plus H. By this statement we mean if R1 equals R, that means initially the body is on the reference level, body is on the Earth's surface, because capital R denotes the radius of Earth. If the body of mass m is moved from the surface, where we can write R1 equals capital R, to a height h, now then R2 can be replaced by R plus H. Therefore, the change in gravitational potential energy, that is delta U, that comes out to be Gmm. Now 1 by R is to be replaced by R1 is to be replaced by 1 by R, then minus 1 by R2 is to be replaced by R plus H. Now see, this will be equivalent to Gmm, and I will write this as capital R, 1 by R. So this is 1, then this comes out to be minus R divided by R plus H. Now this is equal to Gmm by R, this is 1 minus. Now let me divide this term, that is R divided by R plus H, both numerator and denominator by R. अगर हम यहाँ पर R को डिवाइड करेंगे, R से we are left with 1 divided by, denominator को R से डिवाइड करेंगे, R is to be divided by R, that means 1, then plus another term will become H by R. Now delta U is equal to, I will write Gmm by capital R, inside brackets we have 1 minus, this is 1 divided by H plus R whole raised power 1, I can write this as 1 plus H by R whole raised to power minus 1. Now this is Gmm by R, this is 1 minus. Now let me expand 1 plus H by R whole raised power minus 1 by using the binomial expansion. And since R is far greater than H, therefore H by R is far less than 1. Therefore, the only first two terms of this expansion will be significant. Therefore, we can write 1, then minus, this is the binomial expansion, this is 1 minus H by R. Now other terms can be neglected. Now this is G capital M small m by R, and this is 1 and 1 cancels, then we are only left with into 1 by R. So we are left with G capital M small m by R square. This is the required result, but this is Gmm H by R square, but I will rewrite this expression, this is G capital M small m H by R square, but acceleration due to gravity can be written as Gm by R square. With this substitution, delta U comes out to be Gm by R square is G, I can write this as mgh. This is the change in the gravitational potential energy when a body is moved from the surface of Earth to a height h. Now this is